integrating storage into the electric grid. And then April 5th will be Will Paxton, Senior Scientist, Project Lead of Innovation Center, California at Volkswagen Group North America. So Will's going to talk about Volkswagen's essentially plans and efforts in electrifying cars. But today it is a pleasure to introduce Javad Mohammadi. He is a relatively new assistant professor here at University of Texas at Austin, so it's a pleasure to have him speak in front of us today. He's assistant professor in the Department of you were in Electrical and Computer Engineering at Carnegie Mellon, and now he's in the Civil and Architectural and Environmental Engineering School today. So if you talk about at least crossing disciplines amongst engineering, then he's got that, right. So today he's going to talk to us about the digital transformation of our energy infrastructure, try to understand differences between small scale, large scale, grid scale versus distributed scale energy, how we use information, how we use smart technologies to integrate all these systems, including for the role of decarbonization. So understanding centralized versus decentralized systems on the grid. So again, just a little bit of his background. So he's assistant professor here at the Department of Civil, Architectural, and Environmental Engineering here at UT Austin, and he was part of the Electrical and Computer Engineering Department at Carnegie Mellon. And he's also an IEEE senior member. So as you'll learn, his research interests are in multi-agent optimization and machine learning, network cyber-physical systems, and we're going to talk about applications of the power grid today and electrified transportation systems. So with that being said, I will hand the controller.
Thank you so much.
And let's welcome him here. Thank you very much.
All right, thank you, Kerry. Hi, everyone. Great to be here. I'm very excited to talk to you, and I'm hoping that this conversation leads to more conversations with the folks that are on campus. I would be happy to get coffee, meet you in person, and chat more about these slides or anything interesting that you find in this presentation. Also, for the folks online, I would be happy to answer your emails or get in touch with you over Zoom, and we can exchange ideas over there. So I'm going to talk about how our energy system is transitioning and what does it mean in terms of operation, okay? And we are going to talk about what are the two major changes that's going to impact the operation of the future energy systems and how the grid is becoming more and more distributed and how we need more and more resiliency in the system, and how we can leverage both of these trends to make sure that we have a decarbonized resilience energy system. So if you look at how as a society we have come to date, like most of the major economic shifts have one thing in common, and that is the overlap in transport technologies and energy system and communication. So first industrial revolution, that was mainly because of having access to coal, having access to railroad, and also printing machine. Oops, oh, I turned off, no, all good. And the second industrial revolution in 20th century, that was mainly because of having access to oil, electricity, radio and television, and also creation of internal combustion engine. And we are at a point in our history that we are looking at the third revolution, and that is mainly because of having access to internet, having access to abundance of clean energy like renewable energy, and also creation of new means of transportation, like electrified transportation system and autonomous technologies. So all of these changes mean that we are having more connectivity and autonomy in different systems, in different cyber-physical systems. An energy system as a cyber-physical system is transitioning as well. So if you look at how electric grid was built over 100 years ago, we built this system with putting big generators on one end and end users on the other end and putting distribution and transmission systems in between. But now things are changing, right? We are having a lot of small-scale energy resources being added to the system. And a lot of these energy resources, such as electric vehicles, such as small-scale PV systems, they are intermittent, and they're hard to predict. It's hard to predict their output. So that's impacting how we are operating this system. To address the needs of this transition, we need to rethink some of the methods that we put in place for managing the original system. And at the same time, electric system and energy system in general is under a lot of pressure to reduce its CO2 production. On the climate side, really the science is clear. We need to reduce our CO2 emission dramatically by mid-century. And in the support of this, a lot of changes are happening. Also, electric grid, as one of the largest producers of CO2, is expected to remove barriers to accommodate more and more renewable energy system. So we are adding more intermittency and uncertainty to both ends of the grid. And while decarbonization might be still a sensitive issue to talk about, like resiliency is not really. So like as a lot of events have shown us, electric grids are mostly underprepared to deal with extreme weather conditions. Whether it's winter storms in Texas or it is wildfire in California. So operating on low resiliency margins makes us vulnerable to any significant change in the system. And to address this, there are a lot of decision makers that are thinking about addressing these issues. What would be the issues? What are the gaps in the system that we need to address? And that's the need that we are dealing with right now. So really the message here is, while we are trying to reduce our carbon footprint, we should also make sure that we are preserving the privacy, we are preserving the resiliency of the system. So we need to decarbonize with resilience. And if you look at this system, like from one end to the other, you can look at this system from the big generators all the way to the end, and the changes that are happening on each end of the grid require different sets of decision-making tools to make the operation of the system smooth. For example, on the end-use customers, we are having a lot of energy resources being added to the system, and each one of them are very small. Okay, each one of them are like, some of them are kilowatt scale. But the questions that we need to address on that side would be like, how can we leverage some of these small scale kilowatts that are being offered by these clean energy resources and integrate that with the operation of the system? And the challenge here is each one of them are small, so it's really hard to control them. So the question would be like, how would you coordinate these small kilowatts of energy flexibility and make them sizable and make them megawatts of energy resiliency? So coordination and integration would be a big question that needs to be answered on this end. And on the other side of the grid, we are adding more changes, more energy resources, and we are adding more complexity to the other side of the grid. So we need better decision-making models, better optimization methods to solve the problems that comes or that this part of the grid is dealing with. At the same time, some of these resiliency resources and some of these resiliency solutions that are being offered by the end-use customers, we want to integrate them on the other end of the grid. So we need to make sure that we are developing the right set of tools to manage those megawatts of energy resiliency that we can get from the other end of the grid. So really, we need to revisit some of the decision-making methods and optimization procedures that we put in place for this system. And really, the need for like making these changes originates from from various challenges. Like one of the challenges that my group is working on is around data and privacy. So we are adding a lot of decision makers into the system at different scales, and we need data from them. So we don't only need data from big power plants and the big players in the system. We also need data from end-use customers. And you're dealing with huge data volumes, and you're also dealing with heterogeneous data sets. So the question would be like, how would you process those data sets? How would you make the right decisions, given that this data is fundamentally distributed? A lot of these data sets are also owned by different entities, so that some of them are not willing to share the data. So how will you make sure that you are putting the right set of decision-making tools in place? They are privacy preserving and makes people and make parties comfortable with sharing some of this insight with each other. And we would need to have access to some of this data for operating the future energy systems. Another challenge that I think is very important, and we need to think about this, is how to address the growing complexity of the system. Okay, so we are adding a lot of new entities in this system, and entities in this setup, you can think of them as like any homeowner, any smart buildings that can make decisions on its own and can respond to a signal. You can start from that going all the way to the big players like big power plants, nuclear power plants. So you are having different entities at different scales, and each one of them, they're making their set of decisions. And as we're adding these decision-making variables to the system, the problem is becoming more and more complex. So it's harder to solve. So we need to rethink some of the methods that we put in place for solving a simpler problem 100 years ago. And we're also seeing a lot of interdependence between electric grid and other networks, such as gas networks, such as water networks, such as a transportation network. So how do we deal with all of this? So more interdependence means that if you have a failure in one of the networks, that failure can propagate to the other networks. So how would you deal with this? So you have to put the decision-making in place that can manage the complexity that this system is dealing with. And also, when we put this system together, given that we had, there were relatively limited number of entities that were involved, comparing with today's system, a lot of the decision makings were put as a centralized decision making process. So centralized decision making means that every decision makers will share some of their data with a central brain. That brain will process the data, and after solving the decision making process, it will send the decisions all the way back to the parties involved. But as our complexity is growing, we need to leverage the multi-agent information processing methods to make this scalable, make this close to real time. Okay? So if we want to integrate more and more renewable energy system, we need to think about ways of having each one of those renewable energy setups that might be small at scale, have them talk to each other, have them coordinate with each other. So that brings the question as how would you make these agents or entities in this system talk to each other? And multi-agent information processing systems, they have also proven to be more computationally efficient. You can distribute a lot of your computations between multiple entities, and that will simplify the process. That will reduce the computational complexity. And they could be also privacy preserving as well. So you don't need to share all of the information with one central guy. You can process some of this information locally, do that close to the edge, and share insight with other agents or other entities involved. And they're more adaptable too. So you can have a plug and play system. So if a new party wants to play, they can just plug into the system and be part of this game. And they need to be talking to one of these other entities in the system, but they don't necessarily need to talk to a central coordinator. And these issues of distributedness, complexity, and privacy are basically showing up in every cyber-physical infrastructure. It's not only energy system that's dealing with them. And in the rest of this talk, I'm going to focus more on the energy system, but the methods that I will discuss in the next section, they would directly apply to a lot of decision makings in other cyber-physical systems as well. So with that being said, I'm going to briefly discuss the mathematical foundation for one of the methods that my group is working on. And I will keep it at a high level, but please feel free to ask questions. I will be happy to share more details. So you see a lot of multi-agent decision-making and multi-agent problem solving in different contexts, from situational awareness all the way to learning on the edge. These problems appear in different setups, and they appear in different contexts and in different cyber-physical systems as well. And at the core of each one of them, there is sensing that each one of the entities that are involved in this process, and you can call each one of the sensors, each one of the decision makers, even a Raspberry Pi that is collecting some information in the system and is doing some processing, that could be an agent. So the first step would be sensing, and after that would be computing, like doing some local computations, and then communicating with another agent. And there are a lot of ways to set up the system. Okay, depending on the communication structure that you have, depending on the communication capabilities that you might have in a system. So here are 4 examples. You can have a fully centralized system where you have sensors or your decision making directly talk to a central guy, and that will be the central coordinator, and that will be the fully centralized system here on the top. Or you could have this fully distributed, peer-to-peer. Everybody talk to each other. Okay, so there's no need for a center. So this is a fully decentralized setup that nobody needs to be in charge. The way this works is everybody try to take responsibility. They do part of the process, and they would talk to each other. And through that talking and doing part of the process and computing, they would collectively solve a problem. Another setup would be that you have a collection of these nodes or different agents under one umbrella and having a fusion center or having a fusion data processing center in charge, and then those talking to a coordinator. Or those fusion centers, they can talk to each other in a peer-to-peer fashion as well. So there are a lot of setups that we can leverage here, and that will really depends on how much computational power you have and how much communication you have in the system. And this will enable us to leverage some of these existing communication setups that we already built into our system, into our electric grid. And let's walk through a process, and I will discuss here how we are thinking about solving an optimization problem, like a classical optimization problem, in a decentralized way. So if you have an optimization problem, you are minimizing an objective subject to a bunch of constraints. You might have inequality constraints, you might have equality constraints, and instead of dealing with this in this original form, you can solve this problem by finding its first order optimality conditions, taking derivative with respect to primal and dual variables, and that would give you a set of equations. So really what I'm doing here, I'm translating an optimization problem in its original form. It could be any classical optimization problem, by going through an established set of steps to convert that to a set of algebraic equations. And under certain conditions, we can show that this will lead to, if we find a solution for that, we'll have an optimal solution to this problem. But all that's important here is that we are moving away from having an optimization problem into having a set of equations that we are trying to find a solution for. And when you look at this set of equations, you see that these equations, they would have 2 types of variables. They have some variables that are related to each of the nodes or each of the agents. We could call them local variables. And there are some variables that are shared between some of these agents, and we call them global variables. So the difficulty is really dealing with these global variables. And the way to do that is to create local copies of those global variables that are shared among any of these agents, and assign those local copies to each of these agents. So what happens is now each agent has a local copy, and they do their own processing with that local copy, but we design the process in such a way that at the end of the process, those original equations are solved. Also, those local copies are coming to the same value. So those local copies are reaching consensus. So mathematically, we can, when we are formulating all of these updates, we are going to put a term that will make sure that all of these local copies we created, they would come to a consensus. They would come to the same value at the end of the iterations. And we are also solving these equations that we put in, that we want to solve at the end. So instead of solving a problem in a centralized form as an optimization problem, we break that down into a set of equations that we are going to assign to each one of these end-use customers. They're going to do their own thing, and they're going to update the variables, but through updating their variables and talking to other agents, you're going to make sure that all of these local copies are reaching the same value at the end. And also, we are solving these equations. So that's really the intuition behind this method that we are using. And this gives us a lot of creativity. Now we can have different definitions for different nodes. We can cluster a bunch of nodes in the system into under a group, and those groups can talk to each other directly. We can add communication lines. There are a lot of things that we can do here because the structure of this method allows us to have different communication and computation setups. And so really from the technical perspective, yes?
Hello. So can you give an example of when you say that these different sensors are trying to talk to each other or they are exchanging information? What are they talking about? Like what is the information that they are exchanging? I guess that's one question. And what exactly are they trying to coordinate or maximize or minimize? For example, the optimization problem that you were talking about
Sure.
in one application context.
I
Thank you.
have two applications coming up, so if you don't mind, I'm going to answer your question in the context of those two
Okay,
examples.
that's perfect. Thank you.
But that's a great question. That's basically a perfect introduction to my next section. That's great.
Okay, thank you.
Okay, so let me wrap up this first, and then I'll talk about those two examples. So just to wrap up these sections, from the technical perspective, we have integrated constraints into the consensus process. And this consensus process, making sure that these variables converge to each other, you see that in a lot of contexts. Blockchain is a consensus-based, it has a lot of consensus-based protocols. Swarm robotics, they have consensus. So those consensus processes, making sure that these variables converge to the same value, that will appear in a lot of contexts. And making sure that consensus, when they're reaching when they're converging to a value, that value would be the right value for solving your constraint. That would be really the contribution here. And the way this setup works is we moved away from solving an optimization problem into solving a set of equations. And so instead of having the need to have an optimizer, we are just going to deal with a lot of additions and subtractions and those things. So we are basically dealing with the situation that we can implement this on a low budget computation setups. So we can easily have this run on a lot of sensors as well. And this setup is highly configurable. And now let's talk about examples. So I'm going to give examples on two ends of the grid. I would start by talking about the end use customers. One of the prevalent ones that you hear a lot about these days is the electric vehicles. So we're adding more and more of those to the systems. And the question is when you integrate them to the system, what would happen to the system? How can we make sure that they're helping the grid, not hurting the grid? And on the other side, I would have my second example about about the bulk power system. How can we use some of these multi-agent methods to reduce the computational complexity of solving a giant problem for the system as large as the entire US power grid? All right, okay, so let's talk about the scale and the importance of these smaller guys that are being added to the end point of the grid. So we, like a lot of people talk about how these resources are being integrated at a rapid scale, but really what showed us a glimpse was solar eclipse in 2017 in the Northeast. And the power utility, the utility company there, PJM, that was managing part of that grid, was expecting a reduction in the solar power because of the solar eclipse. What they also saw was that the electric demand went down. And what really surprised them was that they didn't really know where that's coming from. And what was interesting was Nest sends a lot of its thermostat to energy efficiency mode. And that was enough to make a huge impact at the scale that was noticed at the grid level. So that shows how impactful these small kilowatts that being added to the end side of the grid are. So as you're adding more and more of those, they are being more impactful. So if you impact them at a scale, you will see an impact that will show up at the gigawatt or megawatt scale. And this is good or bad. So good is good because you can coordinate these small kilowatts. You can leverage them for managing the system. Okay. It's bad because if you have a cyber intrusion and you impact a lot of those nodes, that could be impactful enough to bring down your entire system. But we're going to talk about the good example here. Okay. So why coordination? Why do we need coordination? So to answer that, we need to go back to the basic rule of any power system. And every procedure that you have in electric system, that's basically built on around one basic rule. And that is equality of supply and demand. Okay? Energy system is effectively a supply chain, and that equality of supply and demand is very important in every supply chain. But in energy system, in electric grid, we need to make sure that supply and demand are equal to each other at all times. So that's very important for us. And as we're adding more and more intermittency to the system, as we're adding more renewable generation to the system, preserving that equality is becoming harder and harder. Because now you're having generation that is changing all the time. So now you need to make sure that you're balancing out this generation to make sure that you're capturing these, you're containing these oscillations and they're not impacting your system. So if you have a bunch of resources on the demand side that are coordinated and they can respond to these oscillations and they can balance them out, that would be very impactful. Okay. So what you can do in these setups, you can basically leverage one of the big generators, big reserve generators that you have in the system. You can leverage that for managing those oscillations or those intermittencies. Or you can leverage like a big energy storage. But you can also leverage some of the small scale resources that you have. Each one of them are very small scale. Each one of them are kilowatts. But if you coordinate them, if you make them talk to each other, they would provide enough of a response that can balance out that intermittency. And really the question that's what are they sharing with each other? That really depends on the optimization problem that you're trying to solve. That really depends on the goal that they're trying to achieve. One example of the goal that they're trying to achieve would be they already received the payment from the utility to respond to a situation, to provide a specific level of, like for example, provide a specific level of like a specific megawatt in a geographical area. So you have a lot of different size systems. They come in different sizes, different shapes, and they're talking to each other. Each one of them, they have like limited capabilities, and at any given time, they can provide a specific amount of flexibility. But if they communicate how much they can contribute to each other without sharing their sensitive information, and that communication happens between these agents, collectively, as a set of agents, they would provide the response that's needed. So you can, and that's being done in different fields. You have this concept of think globally, act locally, being shown in a lot of different fields. And really, I think the way the future of energy system will look like, as we are having more and more decentralized system, we need more and more of these multi-agent decision-making processes that a lot of these agents will do things on their own, but they also have the global objective in the back of their mind. And to do that, to make this happen, we need to have this set of adaptive methods that are also privacy preserving as well. So what they're talking about, what they're sharing, that's very important. So if there are, like there might be a setup that some of these nodes, some of these players that are working with each other, they're also competing in another context. So they don't want to share every information that they have. So how would you break that? How would you put that decision-making process in place that they're only sharing insight, not the raw information? And let's look at this in the context of in the context of an example. Let's say that you have a fleet of electric vehicles, and collectively they are trying to reduce the cost of their charging. And you can think of it as a company like let's say Uber. They have a fleet of electric vehicles, autonomous electric vehicles that are sending around for picking up customers. And they want to make sure that the cost of energy, the charging them is also under control and minimized. So really, the goal is to minimize the cost of energy for this fleet. But that's also subject to a set of constraints that will be dictated by each one of those vehicles. So each one of these vehicles, depending on how much mileage they have, how far they go during the day, and how they're being used, they would have different set of constraints. At the same time, we want to really pay attention to that aggregate number. Like in total, like what would be your charging need as a group? And we're going to pay for that group as total. So going back to that principle that I mentioned in the previous section of my talk, you can basically derive those set of equations, and the shared variables here would be those aggregate numbers, because you need all the information from all the agents in the system to calculate that aggregate, okay? And instead of doing that, what I'm going to do, I'm going to create a local copy of that aggregate that each one of these agents, they're going to work with that local copy. And they would sense, they would compute, they would talk to different agents. And in this setup, the communication is really flexible. So they can talk to any set of agents. And at the end of the process, I want to make sure all of those local copies that I created, they would come to the same value. Because remember, I would only have one value for the aggregate load. I won't have like multiple values. If you add them up, they would add up to one number. So all of these local copies that I created of that aggregate value that each agent is working with, I would set up an update in such a way that those local copies will come to the same value. And that's really the beauty of this process, is that you are reaching consensus during the process, but you're also solving a set of constraints that are related to each one of these specific electric vehicles. And if you look at the impact at a scale that this could have, for example, together, if they're collectively responding to the price signal, for example, they can shave the peak and they can fill in the valleys. And that will help the electric grid as well. So they're saving costs, but they're also consuming energy in the time that we have less consumption. And electric utilities, they really like seeing these smooth electric loads because that's easier to manage. And this is, and if you think of like like all the investments that we are making as a nation, like in electric vehicles, how like there are in this new administration, there are a lot of talk about like electric vehicles, how to incentivize people to buy more electric vehicles, how to integrate them. Really, like that's the first layer of like adoption, and like buying those vehicles is really the first step. The next step would be, how would you maximize your investment? How would you make sure that these electric vehicles that people have, they will respond to a signal that would depend on the grid, that will depend on the situation, and they could provide both resiliency and as well as cutting the carbon emission. And this would be impactful at scale. So if you do this at in different states, that would be impactful. We did this analysis for the impact of tax credits in 2019. And you will see the impact of the EV tax credits in 2019 across different states, which will vary depending on the generation mix that they have, but that's impactful. And you will get a significant more impact out of this by coordinating these electric vehicles. And really, the takeaway that I want everybody to have from this example was that it's really important to connect these small kilowatts that are at silos and make them bigger, make them more impactful. And that's where I think we'll see a lot of innovation happening, a lot of new startups working on new methods to create that aggregate impact. We have electricity market on the bulk power system. We can have the same thing on the distribution side, on the end use side as well. So a lot of these end users, they could bundle up and they could create they would create these aggregations, and they could participate and in these type of markets, and they would provide the services that would be much needed in the future energy system. And the application of these methods, my group has explored in different setups. We worked with Southern California Edison and TVA, EPRI, and Oak Ridge, for example, to look at like how we can create economy of scale by leveraging the small capacity that each one of the commercial refrigeration systems offer. So if you look at like the commercial refrigeration system, they're effectively a battery energy storage. Every time that you open the door, the cold air will go out, and you're going to lose lose temperature. And when the thermostat is working, they're basically charging up. So, but there's some buffer in that system. So if you leverage that buffer at a scale, that would be a considerable energy resource that you can leverage for optimizing your system and helping your system. We looked at like how we can build privacy-preserving methods for predicting the loads of different buildings. Each building will do their own set of computations, and collectively they will help each other out without sharing any sensitive information. This project is going on with the help of, with the support of UTES in Portugal program. And we also looked at like how we can holistically optimize a lot of resources that we have in a building, in one building and across multiple buildings. And we are looking into this with the support from one of the largest solar manufacturers in Europe, in Portugal. So now that I've talked about end use side of the grid, like looking at distribution systems and the end use customers and how we can aggregate what they're offering, you can take let's look at the other side of the grid, and you can make a distinction between these two sides of these two efforts by looking at them from the bottom up or top down, really connecting those small kilowatts and creating those megawatts. That's really the bottom up approach. You are starting from the bottom of the grid. You can also look at this decarbonization and resiliency issues from the top-down approach, starting with larger scale generation resources. And if you look at like how electric grid is right now structured, these circles that you see on this map, each one of them is responsible for making sure that supply is equal demand in their jurisdiction, and they're also working with the entities that are under them. And you can think of this system as with the smallest entity being like the smart build, for example, one smart building, going all the way to like one of these being an entity. And they are working with each other to make sure that the supply equal demand equation holds. Okay? But if you are going to solve this problem, if you are managing this grid at a scale, that would be a very large scale problem to solve. Because now you have a lot of decision variables, you have a lot of flexibility being added to the system, so you want to leverage those. But at the same time, every time that you add a new resource to the system, you're adding a decision-making variables to the mix as well. So how would you deal with all of these decision variables that you're adding to the mix? So if you think of like energy system in a simplest form, like in a two-node example, that you are generating power in one end and sending power to the other end to be consumed. So if you were to do that, you will have like different set of like equations and different set of constraints in the system. First, you want to make sure that you are not producing more than the limits of your generation assets. Also, your wire would have limitations, so you would be limited to that as well. And you also want to make sure that supply-demand equality holds. So that would be the basic principle that we are trying to hold here. At the same time, we want to make sure that we are respecting the economical considerations as well. So our preference would be to procure power from the cheapest energy resources, if we can, given the limitation of the system. So you would be dealing with these set of equations. And if you were, for example, to leverage these set of principles to look at this toy example of having a three-node system, that you have different resources and you're trying to provide power to a bunch of homes on the other end of the grid. So the global objective here would be like that the true energy resources that you have would provide enough generation that will cover up that load. So you can think of this as that think globally, act locally concept, that each of these nodes, we would have an entity which would be in charge of that node, managing all the resources that's connected to that node. And locally, that agent will look at like how much energy is being produced there, how much consumption exists in that node, and how much energy inflow and outflow is getting into that node. So basically making sure that making sure that whatever is produced is equal to whatever is being consumed and whatever is sent out, as well as like whatever is being absorbed. And after doing that, they can do that like on their own, but they cannot do that in silo, right? So they need to talk to each other. So in this setup, there is a physical setup that we have to respect. Each one of those nodes are connected to another node. So this is an example that we have to respect the physical limitation of the system, and we have a physical layer that we have to be mindful of. So each one of them will talk to their physically connected neighbors, and they will share like how much inflow outflow they have, for example, right? And that would help them collectively manage the system, and they don't even have to report all the information to a center. You can create like a center, a decision maker for this setup if you like. You can easily add that as another agent that's receiving like information from all the other agents, but not necessarily. But like but really the goal would be to leverage some of the communication structure that you have already built into the system and built originally in the setup. So we are hoping to leverage some of those as well. So really, that's really the mindset here to make sure that we are leveraging that the existing setup as well. And if you, like for example, this, if you were to manage the energy supply in this example, having a 118 node system, which is an IEEE benchmark, I broke this into 2 areas, and each one of them having 4 sub areas, and we looked at like how each one of these areas will talk to each other. And you see 1, 2, 3, 4. And if they have a physical connection, they will talk to each other. If they don't have physical connection, they don't need to talk to each other. But by adding like more communications, you are helping the problem to be solved faster. And we can really solve this problem by taking the same principle, breaking those computations into computations that each of these nodes will solve, and over the course of iterations, each of these variables they would converge to the optimal value, and this value would be the value that would be the optimal value for this problem as well. So you would see that over the course of iterations, we're getting closer and closer to the optimal value. So we are solving this problem as the iteration goes on. So we design this iterative process that is basically breaking down the computations between each of these nodes. They're doing their own thing. They're talking to each other. And during the course of iterations, as they talk to each other, they would get closer and closer to solving this problem. And there are all sort of like theoretical guarantees that we can provide for this setup that I would be happy to send you the link to look into that with more details. And this would also scale to other like problems as well. This would be applied to other problems as well. One of the very important problems that energy utilities solve is making sure the system is reliable. And to do that, they want to make sure that if they lose one element, they can still manage the grid. And they would call that N-1 criteria. For example, if you have this toy example, if you lose one of your lines, you can still manage the system. If you lose another line, you can still manage your system. So you're prepared for a contingency. If something goes wrong, you can manage the system. And you can really leverage that system, like that setup, to solve these kind of problems as well. And this is very, like if you think of like the emergency situation that utilities would be dealing with, like if you had this toy, in this toy example, let's say you lose your wind turbine, for example. So you would dealing with the situation that you will have more demand than your production. So you need to think about this ahead of time. You need to provide enough resources in the system. You need to make your optimization flexible enough to account for that. But this would mean that you're adding more constraint to the problem. So you're making your problem more and more complex. And Department of Energy has recognized this need. So Department of Energy has put together this competition called Grid Optimization Challenge, which looks into solving larger scale optimization problem at a scale, like at a scale of, like for example, 30,000 nodes, and with a lot of constraints, with a lot of variables, and that's a really hard problem to solve. And so the team that I've been co-leading has been participating in this process, and using some of these techniques that I showed you, we have been one of the top teams performing in the U.S. For the past two competitions, and we are going to the competition number 3. But really, the mindset here is like breaking that larger scale optimization problem into smaller pieces, having each one of those pieces being solved by an entity, and having them talk to each other to solve that problem. But in this setup, that would help reducing the computational complexity. And off of that, we got in contact with REN, the National Electric and Gas operator in Portugal, and they were thinking about like modernizing their electric grid. So we are using the same set of principles to help the national electric utility in Portugal to manage that and to look at, to solve those larger scale problems. And these complexities will only increase. Okay, so if you look at like how our energy mix is changing over the years, we're adding more and more renewable energy to the mix. So we're absorbing more and more intermittency to the system, on both at the scale of like megawatts and gigawatts, or at the smaller scales of kilowatts. Okay? So really the future of our energy system will depend on how we're absorbing this intermittency into our system. And to absorb that intermittency, to absorb that uncertainty, we need to show flexibility. So we can provide flexibility by building larger scale energy storages. That's a very effective way of doing that. But like the question would be like, how much will it cost? And the cost of the energy storage is going down, but you have another option as well on the other end of the grid by working with the small scale energy resources and connecting them to create a flexible resource at scale. So, and all that being said, is really we need to like tap into all the resources that we have. So every kilowatt counts. So, and I would be happy to talk to any one of you about like different problems that you see in this energy system. And there are a lot of them that you can solve by taking the same approach, by looking at resiliency and sustainability on different ends of the grid, looking at this, starting from all the way, like starting from the smart building all the way to the larger scale power system. Like there are a lot of questions that can be answered using the same concept. So I would be happy to talk to any one of you about that. And I would be, with that, I would be happy to answer your questions.
Question here. All right, I'll start with a question. So this is about, I guess, coordinating, agents or small scale distributed items on the grid. And today, I have the ERCOT app, or we have independent system operator apps or APIs where I can tune in and I can know what the grid level power is, or I can know what the power level is on the grid. And you're talking about how each node has a model or is updating parameters to know what the total load on the grid is, for example, charging EVs. So how does that fit into how you think, right? Do they have a local model of what the total power flow on the grid is? Do they just get connected to what is, I guess, still like a centralized repository of information, or do they compare those two things? What's the difference between my EV just having the ERCOT app versus my EV trying to calculate what the total load on the grid is?
So even if your EV has an ERCOT app, your EV will still has its own set of specifications, right? It will come to a charging station with a specific level of charging, and you will be staying at that charging station for a specific amount of time. So there would be a local optimization that will happen at your EV level, and that would be specific to you. That would be specific to your needs. But to make sure that that optimization problem is being solved correctly, you need information from other sources. So ERCOT app being one source of information that comes to your EV, but also if your EV was part of a fleet of EVs that you have contract with an aggregator that's providing a specific level of service to ERCOT, you need to communicate with other EVs in that setup, or you can talk to an aggregator. So a lot of these computations will be done at two levels. So you can do, you are going to do computations at the edge, at the agent level, and that would be like given your set of constraints, your set of limitations, that problem being solved. But you also need to think like globally what that means for the rest of the system. What's your contribution? What's your promised contribution? What's your commitment? How you can provide that? And there are really different ways of thinking about this. And one example would be, for example, if ERCOT was directly, if there was a middleman between your EV and ERCOT that was in charge of like selling your services to ERCOT, that middleman is not going to only work with you, it's going to work with a set of other like electric vehicles. So that middleman needs to collect some information with you, but you're not willing to share all of your information with that middleman. So you do some of your computations locally on the edge, given you're not going to share your driving patterns, for example, but you will share other informations about like some of the like your charging level and some information that are masked. And you will share that with that aggregator, and that aggregator would be like processing that information and making decision for this for the entire system. The next level of that would be not having an aggregator at all. So like bunch of neighbors come together, they decide to make a coalition, and they would collectively work with ERCOT, and they're not responding. They're not. They don't have anyone on top of them to be in charge. So collectively, they would talk to each other, and they would provide a specific level of service.
So in this idea, even if me and my neighbors come to some collective, become a cooperative, there's still some entity of cooperation that's between the entire grid and an individual device. Or maybe it doesn't have to be that way, but that's a likely way, or we see that as the most likely way it will be, just because each device is so small, right?
I agree with you.
Is that what you're saying? Yeah.
Yeah, but that's like like building a coalition. That's like a very extreme way of like solving this problem. So like more likely the odds are that you're having like some middleman in place. So these setup or computation methods that we are putting, like that we're working on, it has the flexibility of like doing this fully decentralized, no middleman being involved, or having some level of middleman being involved. So it can accommodate any of those setups. But solving this in a fully decentralized, that's the hardest way of like solving it, because like there's nobody in charge. So you have to make sure that you're avoiding chaos between all of these agents, and they're collectively solving this.
Right. Anything else? So I'll follow up on that. If there's no questions. I'll go back to this question on my way there. So you see that having a middleman, if you will, is computationally more efficient than having none, or do you know that answer?
I don't have a definite answer for that. So that really depends on the setup that you're working in and how much computational resources you have on the edge. Okay. So if you're dealing with a situation that you have a strong processing power on the charging station, that it can do, like that processing unit can do a lot of those computations. Having a middleman could like doing this decentralized could be more effective, but really the trade-off you're making is between computation and communication. So how much computation you are doing locally, how many times you are talking with your neighbors, and each one of them have their own costs. So that's the trade-off that you are making when you are designing a specific decision making for a specific setup.
Right. Okay. Thanks.
Thank you. So I have two questions. The first is about the problem that you were talking about, the top-down problem. Mm-hmm. And you said that in that case, there would be sort of sub-problems that you would be solving, right, at a smaller level.
Yeah.
And you showed it, I guess you also mentioned that there was a IEEE 118 bus system.
Right.
So my question is, for such kinds of, such class of problems where there's a top-down approach, what is the class of optimization problem of these smaller problems? Like, are those straightforward LPs? Because I would assume that if you are solving it for larger grids, things can get pretty messy very quickly.
Right. So that depends on your original optimization problem. If you were solving like the linearized version of the messy problem, like the DC optimal dispatch problem.
Right.
So that would be like those subproblems that you would be dealing with, they would be still LP. But if you were dealing with like AC like version of the problem, which you will have sine and cosine in each of these equations. So those set of subproblems, they would come with sine and cosine. So that would be a non-convex situation that you would be dealing with. So a lot of these theoretical guarantees that we will have, they would start with the convex setup when you have these LP situations. Right. And then they would, some of them would apply to non-convex.
So even within the class of like the convex optimization problems, at least in your cases, are you, do you usually use the DCOPF relaxations, or I also know that there are some tighter SDP and SOCP based relaxations. So do you is DCOPF the go-to, I guess, the model, or have you tried something else?
No, we tried something else too, but for this specific example that I showed you here, the toy example that I showed here, that was DC. So there are two ways you can deal with this. So you can convexify the original optimization problem first, and then you break it down, or you can just basically you can basically have these subproblems, and you can do some relaxations when you are dealing with the subproblems. Okay, but this example that I showed you, that was easy.
Okay, and there's no discreteness involved in this stage, right? There are no integer variables, or do you have some discrete variables as well?
In these setups that I've showed you so far, no, there have been no integer variables for that. But for this, For this grid optimization challenge run by Department of Energy, there were discrete variables because we have unit commitments, and that would come like with binary situation. There are also discrete variables for a lot of other stuff as well.
Okay. I have one more, but I'll wait if anyone has any question, else I'll ask.
Anybody else?
Okay. Yeah. The other one is about resiliency, right? I think I can follow the part where you say that the end nodes can play a leading role in terms of if they talk to each other, they can, have a very strong support system to fight against some extreme events. But at the same time, you mentioned about the N-1 reliability criterions, right? So by what I'm thinking is like for, in terms of resiliency, for example, for Texas, be it the snowstorm or the flooding, the failures are usually correlated in space and time, right? So looking at N-1 is more like, flipping a coin at every asset and thinking, is it going to fail or not? So the failures are independent. So with this approach, like how do you go about measuring the resiliency of the system? Or is there any specific class of resiliency that you are focusing on? Like it can be against adversarial threat or something like that.
So resilience is very interesting. I think, so if you look at NERC, like the North America Reliability Council definition, I think reliability and resiliency concepts, they overlap a lot. So, and we have like N-1 security criteria as one of the basic way, one of the traditional means of like ensuring reliability in the system, right? So if you lose a component, you will still, you have still enough flexibility in the system to make up for that. So going back to your question, I think what's the way we solve that, like the way we solve that N-1 security criteria problem was that each one of them, each one of those situations, when you lose a constraint, when you lose a component, that would give you a set of specific constraints. So we would put that as a sub-problem into the problem. I think I partially answered your question. So if that's not completely answered, feel free to repeat your question.
Yeah, I guess we can.
Yeah, let's chat off. I think
that.
the two of us, we have a lot to talk about, I think.
About coordinated failures.
All right.
Excellent. So if there's anything else, I'll make one more comment. I think beginning earlier in your slide made me think of, obviously outside of my area, but the neuroscience and people thinking about consciousness and what is consciousness, and they often come up with the idea that has been debunked of the homunculus, like there's a central coordinator in your brain and all this information goes to the brain and then the brain tells every part of your body what to do, and then they realize, okay, this is not really how it works. Or that was a really, 2 centuries ago way of thinking, Descartes, mind versus body duality, but really it's all integrated in decision making inside the body and connected to the brain. So you kind of made me think about that here. I didn't know if that's where you were going, right? We have this fully distributed decision-making body, right? Each one of our organs is doing something, it has information, is sending it back to our brain. I don't know, how do you think about any biological analogs?
Let's think about this in the context of like human society, how we have like tried as a society. Each one of them, we have our own skill sets, right? Somebody is like in the, some of us are in the educational business, some of us are like servicing cars, somebody is a real estate agent. There is some set of information that is local to us. We know how to do our job like in a specific setup, like an educational setup locally, but the knowledge of driving, that's like a common knowledge that would be shared between all of us. So that's how we have thrived as a society moving forward. So if you look at these setups, there are like these information setups, usually there is like a common information that would be shared, it would help everybody else, but there's this information setup that would be local to you. So what as we are designing this process is we are trying to contribute to that local information setup, but also while keeping our specific skill set private. I think that's the mindset behind going that. But I think maybe like that idea of having brain was kind of extreme, but like please think of this as in the context of human society, not like one individual, like human body.
Right, well, you put the brain up there, so I went for it. I will state this, so I also give presentations where I say almost what you just said there, which is everybody has some conceptualization of what they think the economy is, but they really have their own interaction in the world, like you said, is your job. But there's common knowledge like driving a car. Or perhaps if we learn physics or engineering here. Common knowledge is laws of thermodynamics, but other people aren't taught that, so it's not common knowledge. So that's I think it's an interesting way to think about how you coordinate. It's based upon the common knowledge that exists amongst all the agents coordinating. So that's, maybe we'll end with that theoretical deep point. So everybody, again, thank you. Let's thank our speaker here, Javad Mohammadi. Thank you very much.
No, thank you, everyone. I would be happy to take your other questions. I will stay for a few minutes.
Put the group on, grid resilience like her.